rocket engine is a black hole, not in the way you think. Listen, by the end of this video, you'll know 3 things that will rewrite how you see the universe. 1. Why accelerating through space erases entire regions of reality behind you. 2. How the math of your spaceship mirrors a black hole's edge exactly. And 3. The chilling reason you can never truly go home again. This isn't science fiction. It's a verified, peer-reviewed truth that most people still don't know. If you've ever looked up at the night sky, you probably think event horizons are reserved for the most extreme objects in the cosmos. Black holes, gravitational monsters from which nothing escapes. But what if I told you that every time you accelerate, every time you press the gas pedal in your car, you spawn a horizon of your own? That's not a metaphor. The equations are clear. Most people believe the myth. The Rindler Horizon is a real physical barrier, like a black hole's event horizon, that can trap objects permanently. Even some science communicators get this wrong. They'll say an accelerating spaceship creates an inescapable boundary in space, a one-way door to oblivion. But here's what they never tell you. The data shows something completely different. According to Misner, Thorne, and Wheeler's 1973 textbook Gravitation, the Bible of Relativity, the Rindler Horizon is observer-dependent. It exists only from the perspective of the accelerating observer. To someone floating in space, not accelerating, there's no horizon at all. Nothing there. The moment you stop accelerating, it vanishes, like it was never real. Unlike a black hole's event horizon, which all observers agree is there. So, is it just a coordinate artifact? A mathematical illusion? Not exactly. Because even though the horizon disappears when you stop accelerating, while you are accelerating, it has real consequences. The Unruh effect proves that an accelerating observer detects actual thermal radiation, as if empty space is boiling with particles. That's not nothing, that's a physical prediction, and it's been verified, theoretically at least, but more on that later. Now let's talk about the symmetry that changes everything. Einstein's equivalence principle. In 1916, he realized that standing on Earth's surface is locally indistinguishable from accelerating through empty space at 1g. If you're in a windowless room, you can't tell if the floor is pushing up because of gravity or because you're in a rocket firing its thrusters. That's the foundation. But here's the twist. Gravity on Earth is static. It doesn't change over time, but sustained acceleration, it's cumulative. You keep going faster and faster, and because of relativity, that constant thrust warps your perception of spacetime progressively. After a while, your experience of reality diverges from everyone else's. You start seeing horizons that no one else can see. The math is straightforward. For a constant proper acceleration, the Rindler horizon forms at a distance d equals c2a behind you. At 1g Earth's gravity, that's exactly 1 light-year. Think about it. Everything more than 1 light-year behind your accelerating ship is causally disconnected. Light from those stars can never reach you, not because it's too slow, but because the geometry of spacetime itself forbids it. Now, isn't it strange that the exact distance where a black hole event horizon sits is mathematically identical to this? The surface gravity of a black hole, the acceleration an observer would feel hovering near it, determines its horizon radius. And the Rindler horizon's distance is computed the same way. That's not a coincidence. That's the hidden symmetry Einstein's equations demand. But wait, if the math is identical, does that mean an accelerating observer should see radiation from the horizon? Exactly. In 1976, William Unruh showed that an accelerating observer detects a thermal bath of particles. The temperature is T equals h/2 pi c kb. For 1g, it's 4 times 10 to Kelvin. That's 20 billion times colder than the cosmic microwave background. Undetectable in practice, but theoretically certain. Another myth, some claim this radiation would burn accelerating astronauts alive. The truth, at 1g, it's so cold it would absorb heat from the astronaut. To reach a single Kelvin, you'd need an acceleration 5 orders of magnitude greater than the LHC's, and even that's a trillion times too small. So no, you won't get fried. But the deeper question remains, if the radiation is undetectable, is it real? Let's dig deeper into the weirdness. In 1976, John Bell proposed a famous paradox. Two identical spaceships accelerate identically, maintaining the same distance in their original frame. Intuition says the string connecting them stays taut. Relativity says it snaps. Because in an accelerating frame, simultaneity is warped. What each ship considers now at the other's location shifts continuously. Space itself stretches. That snapping cable reveals something profound. Acceleration doesn't just change speed, it restructures the very fabric of simultaneity. In your accelerating ship, events that seem simultaneous to you are not simultaneous to someone moving at a different velocity. And because you're constantly changing velocity, your definition of now across space keeps warping. That's why the horizon forms. Now the connection to black holes becomes eerie. Stephen Hawking and George Ellis showed in 1973 that the mathematical structure of the Rindler Horizon is locally identical to a black hole's event horizon. Near a black hole, time dilates infinitely at the edge. For an accelerating observer, something similar happens. The past light cone tilts until it forms a boundary where signals are infinitely redshifted. Identical geometry. That's why Hawking radiation and Unruh radiation share the same theoretical foundation. Both arise from the quantum fields near a horizon. A black hole horizon radiates at a temperature inversely proportional to its mass. The Rindler horizon radiates at a temperature proportional to the acceleration. They are two sides of the same coin. So why has no one ever measured the Unruh effect? Because the required acceleration is astronomical. To reach a temperature of just 1 Kelvin, you'd need 5 times 10 ms2. The LHC accelerates protons at 1014 ms2, still 5 orders of magnitude short. Some physicists argue it may be fundamentally unobservable by third parties, tied to the observer's own frame. A paradox, real only for the one accelerating.